guys to another video for chemistry. In this particular video, we are going to cover how to balance chemical equations. Now, there's a couple of things that we need to cover before we start with the practice. And the first thing is law of conservation of mass. It states that mass can't be created nor destroyed. And also, it gives us more information in regards to the reactions themselves. So law of conservation of mass in chemistry is applied in the sense that it tells us that the mass of the reactants is going to be equal to the mass of the products. So we're not going to gain, we're not going to lose mass, we're going to have the same amount from the beginning to the end of the chemical reaction. Of course, that is assuming that our chemical reactions are taking place inside a closed system and then there's no interference of any kind, which is like in a perfect world situation. Sometimes we don't see that in lab, but there's always, of course, an explanation as to where most of that mass could have gone to. So let's go ahead and get started. So for balancing equations, first thing we need to learn is a few important terms. And some of these terms you might already be familiar with. So the first one is going to be reactant, second will be product. Now, the reactant is the compounds that we start with at the beginning of the reaction. The products will be what is formed, the end result of that chemical reaction. So on a chemical equation, we're going to have the reactants on the left side and the products on the right side. And that's simply the standard that we go by. Now, when we write chemical equations, we're going to have two different pieces of information, aside from, of course, the symbols that represent the elements. The first is going to be the subscript. And that is that small number that you see here on the molecule for water. The subscript specifically tells us how many atoms of that one element are present in the molecule. So again, subscript tells me how many of that element are present in the molecule. So the H2O tells us that there are 2 atoms of hydrogen and 1 atom of oxygen. If you don't see a subscript for a particular symbol, assume it's 1. We just simply don't write it, okay? Now, the other set of numbers that is going to give us information is going to be the coefficient, okay? Now, notice they're not, 1, first the same size, and 2, they're not giving you the same information. The subscript is going to tell us how many molecules there are of a particular chemical. So it doesn't really give us information as to what the setup of the molecule is. It just tells you how many of such molecules there are. So here we have that 3. And if you notice, it's kind of like in your algebra classes, that number that's in the front of like a parentheses that tells you how many there are of everything inside of the parentheses. It's kind of like the same idea here. So that 3 tells us that there are 3 water molecules. Again, don't confuse the two. They give you different pieces of information. Okay, last thing that we have to learn before we get into the actual balancing. State symbols. We're talking about the states of matter. Here we have a list of all 4 that you will encounter. S for solid, L for liquid, G for gas, and AQ for aqueous. And really aqueous just means that that particular compound has been dissolved in the water, so it's in solution. Okay, so that's really all it represents. And again, they tell us the state of matter that your particular compound is present within the reaction. And that's important to know because 1, it helps us to realize what kind of compound you're talking about. It's not the same thing as with the solid with the gas. It also allows us to make predictions as to will we have a precipitate, which is we'll learn a little bit later on, but it's a solid that is formed from 2 solutions. So all of those pieces of information are going to give us kind of an insight into what to expect during the chemical reactions. So while we don't always write the state symbols inside of a chemical equation, it's good practice to have it. It is good information, and they should technically be on the chemical equation. So on a chemical equation, this is what it would look like. The ones that are shown in blue on screen, those are the state symbols. All right, so let's talk about what is an unbalanced equation. Here on screen, this is incorrect, okay? I'm just giving you this an example. We have the reactant side on the left and the product side on the right. It tells us with little particle diagrams that we have one carbon atom, 4 hydrogens, and 2 oxygens. Now, the law of conservation of mass tells us that the reactant side must be the same, equal to the product side. So if you start with 1 carbon, you would expect to see 1 carbon on the product side. And looking at our example, that would be correct. We got 1 carbon on each side. So carbons are good. Now let's look at the hydrogens. There are 4 hydrogens on the reactant side that we started with, but on the product side, there's only 2. So that right there is violating the law of conservation because you can't just make 2 hydrogen atoms disappear. The next part at the very bottom says 2 oxygen atoms versus 3 oxygen atoms. So also another example of violating the law of conservation. We can't start with 2 oxygens and somehow end up with 3. That's not a thing, right? It's violating the law of conservation. So we know that this is not balanced correctly. Okay, so now let's look at what it should look like. So the way we, in a way, fix an equation would be with adding coefficients. Remember those numbers that go in the front of a compound that tells us how many of them we have? Well, I'll show you guys a very easy process to go about it, but that's pretty much what we're doing here. We're realizing that we were missing 2 oxygens, and we were also missing 2 hydrogens, yes. So by us adding coefficients to the beginning part of a compound, we pretty much fix what the issue is of the law of conservation. So let me show you exactly how you determine which coefficients go where, okay? So let's look at an example first. And I want us to follow this pretty much the same rules. The first rule, in order to balance a chemical equation, is going to be to make a list. So 1, make a list. And I want you guys to, from this point on, always check if your chemical equations are balanced. Sometimes they won't be, and you will be expected to balance them from this point on. Why is that important? Well, later on, we're going to learn about stoichiometry, and if you don't have a balanced chemical equation, all of your calculations will be done incorrectly. Or if you do the balancing wrong, all your calculations afterwards will be incorrect. So balancing is one of those chemistry skills that you have to know how to do, and you have to master them. And again, just like everything, it just comes with practice. So let's go ahead and start with step number 1, which is making a list. Personally, I like to draw a line right underneath where the arrow is, which just tells us like that's what is being produced, because I like to keep both sides separate. And I'm going to make my list. The first one's going to be aluminum and oxygen. And all I'm making is a list of the elements that I see present in each of the compounds. Okay, so I see an aluminum there, and I see an oxygen here. Now, I like to write down the list right underneath where the compound or the element is located, just because it keeps it really, really organized. But you're more than welcome to change the setup. Just make sure you make a list, okay? Now, we know that the subscript is going to tell us how many of each element there are. So that aluminum says 2. So there's 2 aluminums. There's an oxygen, and it tells me that there's a total of 3. So all I'm making a list is of how many I see, okay? So on the product side, there is 1 aluminum and 2 oxygens. Now, law of conservation of mass tells us that these 2, reactant and product, should be the same. They should be equal to each other. So if I start with 2 aluminums, I should have 2 aluminums at the end. And I don't, right, on my example. So what I'm going to do is that I'm going to multiply my entire compound by a coefficient. So how can I turn the 1 into a 2? Well, 1 times 2 gives me 2, right? So there we go. We multiply a 2. So the coefficient for aluminum would be 2. Now let's look at my oxygens. Now my oxygens here, we started with 3 and we ended with 2. So we have a problem here because I can't really multiply, and we're talking about when I say multiply, you can only multiply by whole numbers. You can't do decimals because there's not like a half molecule. It's just full molecules, so it has to be a whole number. Started with 3, we ended with 2. What can I do here? Well, I could multiply, let's say, my larger number, right, by, let's say, 2. Why am I skipping over 1? Well, because if I multiply anything by 1, it's just still going to give me the same number, and that defeats the purpose. So right here, I'm going to multiply the 3 times 2 to get 6. Now, the reason I did that is because I know that I can multiply 3 and 2 by anything to get them to be the same number aside from each other, right? So let's go ahead and do that. So 2 times 3 gives us 6. So this oxygen got multiplied by 3, so that means that its oxidation number is now 3. I'm sorry, its coefficient is 3. All right, so my oxygens are good. However, let's go back and look at those aluminums. They right now seem to be matching, but there's an issue here. See how that aluminum and that oxygen at the very beginning are together in a compound? Whatever I do to the oxygen affects the aluminum. So if I multiply down here on my list the oxygen times 2, I also have to multiply that aluminum times 2. And that changes the game because now there's 4 aluminums to begin with. So that means I have to go back to the product side and fix that aluminum because now the aluminums don't match. It says aluminum 4 at the beginning and 2 aluminums at the end. That can't be. So instead of multiplying by 2, I can multiply by 4. 1 times 4 gives me 4. So therefore, the coefficient on the chemical equation would no longer be 2, but instead it would be 4. So my coefficients would be 1, because I didn't do anything to, oh, I'm sorry, not 1, 2, right? Because I multiplied by 2. And then 4 under the aluminum, and then 3 for the oxygen. So I'm just going to go ahead and rewrite this on the side because it looks really messy. So it would be 2Al2O3 yields, arrow, 4 aluminums plus 3O2. That would be my new chemical equation that is now balanced. Okay, let's look at another example. Step number 1 is always to make a list, right? And I just realized I didn't give you the whole list, so I'm going to write it this time. All right, so I'm going to make a list. Draw your line to split up. I'm going to make a list. I see a sodium, and there's only 1. I see an iron, and there's only 1. I see chlorine, and there are 2 of them. On the product side, there is 1 sodium, there is 1 chlorine, and then there is 1 iron. All right, so let's see how we can fix this. So the problem seems here to be chlorine. And just go one by one. 1 sodium at the end, at the beginning, 1 sodium at the end. 1 iron at the beginning, 1 iron at the end. 2 chlorines at the beginning, 1 chlorine at the end. The chlorines don't match, so that means I gotta fix the chlorines. So if I started with 2, I should end with 2. So what number can I multiply 1 by to get 2? So hopefully we can do that quickly in our heads, and that answer would be 2. But remember, because the sodium and the chlorine are together in the same compound, what you do to chlorine affects the sodium. So we need to make sure that we are multiplying also that sodium by 2, again, because they're part of the same compound. All right, so I fixed my chlorines. But whenever I multiply that chlorine by 2, it affected the sodium that was with it. So now I'm saying that there were 2 sodiums at the end, and that's a problem because at the beginning, there's only 1. So I have to go back and fix that. So a lot of the times when you're balancing, you're having to go back and forth to try and fix both sides, okay? And don't be scared because many of the times you will actually have to go back and forth, back and forth, back and forth until you get them all to be matching because of the law of conservation, right? All right, so I multiplied my sodium on the reactant side times 2 to get 2. So now let's check our numbers one more time. 2 sodiums, 2 sodiums. 1 iron, 1 iron. 2 chlorines, 2 chlorines. So that number that you multiply by is the coefficient. So that initial sodium, we multiplied by 2, so its coefficient is 2. The iron chloride, we did not really do anything to it, so we just leave it alone, right? Because we didn't multiply this section right here by anything, so it just stays as, 1. The sodium chloride, we multiplied by 2, so its coefficient is 2. And then the iron at the very end, we did not do anything to it, so it's just going to stay the same. So our coefficients are 2, 1, 2, 1. Alrighty, so these have been pretty simple and straightforward chemical equations. And if you notice, we were just talking about binary compounds. So, warning. What happens, right? This is a question. What happens when we have a polyatomic? What if we're talking about a ternary compound? Well, we got to do some extra stuff. And it relates kind of like to algebra, so this is not like brand new information to you guys. So when we're balancing chemical equations, we have to remember two things. To treat polyatomics as an entire unit, and we cannot change the subscripts because the subscripts have already been pre-established based on either ionic compound rules or simply our covalent compounds already have a specific structure. So we cannot, never, ever, ever, ever change the subscripts once they've been given to us. Okay, so that's important. Let's look at an example that includes polyatomics. Same process, okay? Make your list. So I'm going to do that. I see an lead. There's only one. I see nitrogen and I see oxygen. Now, just like in algebra that you have that distributive property, here would be the same thing. That subscript outside of the parentheses, the little 2, tells me that there's 2 NO3s. So everything inside of the parentheses has to get multiplied, okay? So that tells me that there are 2 nitrogens and a total of 6 oxygens, okay? Again, because we are distributing that subscript into everything inside of the parentheses. Let's keep going with our list. We have potassium and we have iodine. Potassium, there's only 1. Iodine, there's only 1. Let's go to the product side. We have Pb, there's only 1. We have iodine, there are 2 of them. K, there's only 1. Nitrogen, there's only 1. And oxygen, there's 3. All right, so let's look and see where we can start. My recommendation will always be to leave the oxygens until the very, very end. Usually they work out by themselves, like as you're doing your calculations. That's just like a personal tip. You don't always have to wait until oxygen's to the very end, but I for sure would not start with them. So let's go ahead and look at what else we could fix instead of oxygen, because that one's obviously off. So lead, there's only 1 of each side. Nitrogen, there's 2 on the reactant, but there's only 1 on the product. So let's go ahead and fix that. And again, there's no right way of where you should start. With practice, you'll just be able to kind of like glance at it and be able to tell where you're going to start. And right here, I just went ahead and multiplied my entire KNO3 times 2 because if I started with 2 nitrogens, I should also end with 2 nitrogens. And since I only had 1, I multiplied by 2 to get 2. So again, because nitrogen is part of a compound, what happens to nitrogen affects everybody else in its compound. So that's why I multiplied the entire thing by 2. All right, so that would give us 2 and that would give us 6. So let's look at our numbers again. 1 lead on each side, good. 2 nitrogens on each side, good. 6 oxygens on both sides, good. See, remember how I told you oxygens usually kind of like just fix themselves? It's always great. And then let's look at a potassium. We started with 1 potassium, we ended up with 2. So we got to go back to the reactant side and multiply that by 2 to also get 2. And because potassium is part of a compound, what I do to potassium is going to affect our iodine. So I'm going to multiply that one as well by 2. Okay, so now I have 2 potassiums on each side, which is also great because I also have now 2 iodines on each side. So all of my numbers match. We are almost done, right? After we make our list, we need to multiply. And then the numbers that we multiply is what becomes the coefficient. So to the first compound, we didn't do anything, so it stays by itself. Ki, we multiplied it by 2, so its coefficient becomes 2. Lead, 2 iodine, we didn't do anything to it, so it's going to stay by itself. And then we have a potassium nitrate. We multiply that entire compound by 2, so its coefficient becomes 2. Alrighty, guys, so let's go ahead and continue on with writing chemical equations. And we're going to take it a little bit further down this time into kind of like information we've learned before. So we're going to write down our chemical equations from word problems and also balance. So here on screen, you have some important information that we've learned in previous videos about ionic compounds and covalent compounds. The first thing remember about ionic compounds is that they're made up of a cation and an anion, meaning a metal and a non-metal. And there's a lot of rules that go with that. We have things like the oxidation numbers need to equal to 0. We also have Roman numerals that tell us information about the transition metals, all that good stuff. So if you don't remember how to write ionic compounds, make sure you go back, find that video that we cover that information, and you review it. Because on this video, I'm not going to go really in depth into why I'm writing the ionic compounds the way I am. It is expected that we know how to do that by now. Now, for the covalent compounds, they're only made up of anions, meaning non-metals. And remember, the reason we use prefixes like mono, di, tri, tetra is because they're all going to have a negative charge. And you can't really make negative charges somehow become 0, right? And another thing that we need to remember about covalent compounds is diatomic molecules. Remember, those are the ones that come in twos, and those are the ones that when they're by themselves, you will have 2 of them. So on any word problem from here on that you see something like oxygen gas or nitrogen gas or iodine gas, like any of the ones that are listed here, we mean like oxygen gas really represents O2, like oxygen with the subscript of 2. Last thing I will say before we get started, always use empirical formulas. And if you forgot, make sure you go back and review. But empirical formulas is the lowest ratio possible of any given formula, specifically for our covalent compounds. So let's go ahead and look at a problem. I'm only going to go through one. I will post another resource on our Schoology course that will give you like a worked out problem, color coded and everything. And just like before I told you with balancing, it just requires practice. So let's go ahead and get started. The problem tells me that we start with lead 2 nitrate. It reacted with potassium iodide and it produced potassium nitrate with lead 2 iodide. So that sounds really complicated, but it really isn't. So the first thing I want you guys to realize is how many compounds we're dealing with here. So let's read through the problem one more time. It says lead 2 nitrate. That's a compound. It's reacting with. So anything that says reacting with, that means that that's like a plus sign. So it's adding to something else. It's reacting with potassium iodide. That's another compound. To produce. Now this is important. If a problem says to produce or to yield or results in or something like creates, anything that sounds like that, like it's making something new, that represents the arrow on the equation, okay? It's producing potassium nitrate. That's another compound. And it's a plus sign, lead 2 iodine. So here we have a total of 4 compounds that we need to write down. So again, I'm not going to be so particular on this because I expect you guys to remember how to write compounds. So again, make sure you go back through those lecture notes or lecture videos. So lead 2 nitrate. Lead is Pb. And Pb has a charge of plus 2 because the Roman numeral tells me it's 2. I'm going to write it here underneath. And nitrate. Nitrate ends in ATE, so that means it's a polyatomic. So I'm going to find it on my list of polyatomics here on the left. And it tells me NO3 with the charge of minus 1. So NO3 minus 1. It's reacting with potassium iodide, Ki. And based on their location in the periodic table, I know that they have the following charges. It's going to produce, remember that's the arrow, and then potassium nitrate. Potassium is K, nitrate again on my list of polyatomics is NO3 with the charge of minus 1. And the last part of the equation tells me that it is lead 2 iodide. Lead is Pb. Roman numeral tells me its charge is plus 2. In iodide, based on the location in the periodic table in group 7, I know that it has a charge of minus 1. Now, because all of these compounds are ionic compounds, their charges must equal to 0. So I'm just going to go by very quickly and figure out how many of each I need to make them equal to 0. Okay, so remember, add more of each that you need to make them equal to 0. Potassium iodide, those are already equal to 0, so those are good. Potassium nitrate, they equal to 0 plus 1 minus 1, so those are good. And then PbI, well, I need another iodine, so that means subscript 2. Okay, so here on screen, I'm going to erase my charges because I've already made all of my compounds equal to 0, so I don't really need the charges anymore. All right, so this is my chemical equation. However, like I told you guys before, we need to make sure that we always balance. And you can only know if it's balanced if you actually check. So remember, our first step is always to make a list. So that's what I'm going to do. PB1, N, and O. Remember, I told you guys before that if there's a subscript and there's parentheses, we got to distribute. So 2 times 1 for nitrogen is 2. 2 times 3 for oxygen is 6. We move on to the next compound and we have 1 of each. Now we move on to the product side. We have 1 potassium, 1 nitrogen, and 3 oxygens. Last compound, PB, there's only 1, iodide, there's 2. Okay, so now let's look at our numbers. Let's look where we don't match up. Leads are good, nitrogens are not, oxygen is not matching, potassium is matching, iodine is not. So like I told you before, don't start with oxygen. That one tends to fix itself, so don't start there. So if we can't start on oxygen, let's go ahead and just start with iodine. So the problem here tells me that we started with 1 iodine and we ended up with 2. That can be, that's violating the law of conservation of mass, so I need to multiply. I'm going to multiply this iodide by 2 to make them equal on both sides. And because iodide is part of a compound, I need to multiply everything in that compound by that 2. Now, I have fixed my iodine, but created a new problem because my potassiums don't add up. They don't match up anymore. So I started with 2 potassium, so I better end with 2 potassium. So I'm going to multiply it by 2. And because potassium is part of a compound, right, what I do with potassium will affect everybody else in that same compound. So I got to multiply everything in there as well by 2. So let's look at my numbers. 2 potassiums on each side, good. And look at that. The nitrogens fixed themselves and the oxygens, as usual, got fixed in the process of me fixing the others. So now that all of my numbers match up, we're pretty much done, right? So let's go back and add right in the coefficients. I'm going to do it in green. So that first compound, PbNO3 parentheses 2, we didn't multiply by anything, so it stays by itself like that. Potassium iodide, I multiply that compound by 2, so its coefficient becomes 2. That product side, KNO3, I multiply that compound by 2, so its coefficient becomes 2. And that last compound, I didn't do anything to it, so it's going to stay by itself.